Welcome to The Explainer. Today, we're diving into a real engineering detective story. We're going to look at how a super fundamental piece of electronic physics, the MS capacitor, actually unlocks one of the most vital modern tools we have, biochemical sensors. This is exactly how things like modern continuous glucose monitors and digital pH readers work. It's fascinating. So let's dive right in and see exactly how electrons and ions learn to speak the very same language. Here's a quick roadmap of where we're headed today. We'll start with the basics of MIS capacitors, look at the three charge states, cover capacitance and threshold voltage, and then touch on energy bands and work functions. After that, we'll see how this evolves into EIS sensors, and finish up with detecting ions with voltage. Let's get to it. All right, Section 1, the basics of MIS capacitors. Let's introduce the star of our show, the MIS capacitor. That stands for Metal Insulator Semiconductor. It's essentially this layered sandwich that acts as a field effect device. You can think of the applied electric field almost like a traffic light system. When you apply a voltage through that top metal gate, the resulting electric field permeates the insulator and actually modulates the charge distribution in the semiconductor down below. This forces the device through three very distinct states: accumulation, depletion, and inversion. Moving right along to Section 2, the three charge states. Now, accumulation and depletion are definitely important, but the real magic, that happens during the inversion condition. This is this wild state where the charge at the very surface of the semiconductor completely flips its sign compared to its natural resting state. And forcing the surface charge to flip is literally the operational key to how these field effect devices function and switch. But to actually get to that inversion condition, we need a very specific amount of force. And that brings us to the threshold voltage, which you'll usually see written as VT. This is the exact electrical tipping point. It's the precise voltage required at the gate to successfully trigger that inversion condition in the semiconductor. I want you to keep this specific metric in the back of your mind because I'm going to tease right now that this exact tipping point is the absolute secret to how our biological sensor works a bit later on. Section 3. Let's talk capacitance and threshold voltage. So, you might be wondering, how do these abstract physical states translate into data we can actually measure? Well, we map it out on a capacitance voltage or CV curve. On the vertical axis, we've got capacitance, and on the horizontal, the gate voltage. And notice how it's not just a flat, boring line. As we sweep the voltage from negative to positive, we get this dramatic slope that maps perfectly to those three charge states we just talked about. To boil the rules of that graph down really clearly, our device hits maximum capacitance during the accumulation phase, it hits its minimum capacitance during the inversion phase, and right in the middle, during depletion, we see this rapid transition. The exact point where it levels off into inversion, that is governed by our threshold voltage. The big takeaway here is that manipulating the gate voltage dictates the electrical output in highly predictable, mathematically strict ways. It's a beautifully controlled system. Okay, Section 4, energy bands and work functions. To really get why that threshold voltage behaves the way it does, we have to look at the physical properties of the materials themselves. This energy band diagram visualizes the energy levels of the electrons in our metal on the left and our semiconductor on the right. Notice that distinct gap between the two? We call that the work function difference. Because we are using two completely different solid materials, their native energy states just don't perfectly align. And that mismatch directly impacts our math. As we can see in this equation, the threshold voltage VT is not some random number. It's directly dependent on that work function difference represented by delta phi ms. This actually tells us something profound. The physical, solid materials we choose to build our capacitor with dictate the device's baseline electrical behavior. The metal we pick literally locks in our threshold voltage. Which leads us to a massive engineering cliffhanger. If our metal gate permanently locks in our device's electrical behavior, how on earth can we use this rigid electronic physics to detect fluid, dynamic chemical biology? And that brings us to Section 5, evolving to EIS sensors. The solution to that cliffhanger is honestly shockingly elegant. We just completely get rid of the rigid metal gate. Seriously. In a standard MIS device, that metal gate's work function never, ever changes. But in an EIS device, which stands for Electrolyte Insulator Semiconductor, we swap the M for an E. we replace the metal with a dynamic reference electrode immersed in an ion-sensitive test solution. So, our physical structure gets a major upgrade. We still have the semiconductor and the insulator at the bottom, but on top, we deposit an ion-sensitive layer, and sitting right above that is our liquid electrolyte solution. That's the actual biological sample we want to test. By dropping a reference electrode into the liquid to apply our gate bias, ion exchanges right at the interface create a totally unique potential. And critically, this potential is directly proportional to the specific ion concentration in the liquid.
Finally, Section 6, detecting ions with voltage.
Let's pull all this together and see how these chemical changes alter our initial math. Remember how simple the MIS structure was? Well, our new EIS setup creates a much more complex potential stack. For our electrical signal to actually work, it has to run a kind of obstacle course. It starts at the reference electrode, passes through the solution, crosses the ion-sensitive membrane, moves through the insulator, and finally reaches the semiconductor. A whole series of potential differences develops across this entire system. Because the signal has to cross all those new chemical layers, our threshold voltage equation gets a serious update. Check out the new terms. We have the potential of the reference electrode versus the solution, which is a constant. We have the potential between the insulator and the membrane, also a constant. But right there in the middle, we have the membrane potential, delta phi sub m. This term is ion-dependent. It actively varies based on whatever we're testing. So because of the test solution, the membrane potential mathematically modifies the overall threshold voltage of the entire device. And here is the absolute visual eureka moment. Because the chemical ion concentration in the liquid directly modifies the threshold voltage, changing the fluid actually physically shifts the entire CV curve left or right along the voltage axis. We just measure that shift, that delta V, and suddenly we know exactly what's happening in the chemical solution. We are literally reading biology as pure, measurable electronic data. It's brilliant. It's honestly mind-blowing when you take a step back and look at what we've done here. We took a rigid, mathematically strict field effect device, swapped out a single solid metal layer for a liquid interface, and created a literal bridge between fundamental physics and dynamic biology. It kind of leaves you wondering, if swapping one single layer turns a basic capacitor into a highly sensitive chemical sensor, what other incredible microdevices might this principle make possible in the future? Thank you so much for joining me on this explainer.